Let me briefly show you one last string matching algorithm that brings in a different idea. That's the Rabin Karp algorithm. I'll go through this in much less detail. In a way, the only thing that's left open to improve on is the space. We had both KMP and Boyer-Moore needed at least as much space as the pattern on top of the pattern. So at least they needed theta of m space beyond the pattern. So what could we improve? The question is, can we somehow, apart from storing the pattern in the text, which we need, can we somehow get away with even less space? The answer is yes. And it's a neat idea that we haven't really touched on in this module, but I think it's worth knowing for any computer scientist. That's the idea of hashing. We will use this in this case. In general, a hash function is just take a complex object and map it down to a small number, taking into account that because there's many complex big objects, you may map several of them to the same hash code, the same hash value. So it's something like it's like a fingerprint, but we tend to think fingerprints are unique for all humans, so it's not a good name. It's a lossy fingerprint. All right. So what we'll do here is we'll take a hash of the pattern and then take hashes of pieces of the text. And if the hashes don't match, then we know that there's no match. That's the idea. If the hashes match, we don't know for sure because there could be several strings that have the same hash. So we still have to check in that case. That's the gist of it. The examples in this subsection will be with numbers, so digits as the alphabet, just because that's a bit more natural for the hash functions that we'll use, but it works without any change with characters. Remember that for computers, characters are converted to numbers anyways. So we could use a hash function like this one, just take x modulo some prime number, 97. So the hash value of the pattern is 95. How would we use this in pattern matching? Well, we take the first 5 characters of the text and compute its hash. That's not 95. And this is not 95. This is not 95. So for all of these shifts, by just looking at the hash, I can conclude it is not a match. So far, so good. At some point, so it's a bit tough to trace, but if you put in the dividing lines, you see this is an occurrence of our pattern. In this case, the agreement of the hash is not a spurious hit. It's an actual occurrence of the pattern. That's the idea. All right. If we directly implement this, we might come up with something like this. So there's a black box that computes the hash for now. I apply this once to the pattern initially. And then for every guess, I apply it to the portion of the text from I up to I plus m minus 1. So it's the portion of the text that could match the pattern. I guess this is a mistake here. It's probably nicer if I would write this with round parentheses, but OK. We compute the hash. If the hashes agree, I still have to check if there's an actual occurrence. And otherwise, I continue. The code is correct. It does what it's supposed to do. Unfortunately, for the type of hash functions that I looked at, this here, for example, you essentially would have to look at all the characters in the text to compute the hash. So we compute the hash, look at all the characters of the text portion, then use the hash. We might as well have just checked the text portion against the pattern with, like before in the brute force algorithm. So as given, this is not really useful. The trick comes in that there are some clever hash functions that are good enough for this purpose, but can be computed more efficiently. And that's based on taking numbers like this, modulo prime, that's the hash functions we look at. And these are good enough for that purpose. I'm just claiming that now without proof. If we had a hash before, and we now want to get rid of the 4 and add a new character at the end. We can compute that by taking the old hash, subtracting the first digit in a way, and then adding the 6. So in the obvious way, in decimal notation, you would do it like that. That's the first line. Now, because we're computing everything at the end modulo 97, you can pull the modulo 97 inwards. That's modular arithmetic 101 that you may remember. So instead of doing this large multiplication here, we can use a small one. And instead of doing this subtraction on the full pattern length, we do it on its hash, which we have from before. So we can do all these computations with fairly small numbers. In particular, essentially independent of the length of the pattern, it just depends on the size of this prime number. And so that's the trick of fast rehash. When you look at the code, the key bit here is this rehash computation. And it does what the example has shown on the previous slide in general. It does a few multiplications, subtractions, but they all involve small numbers. And by small, I mean around the alphabet size and around this prime number size, but you can work it out so that they stay in a small range independent of m, the length of the pattern. If you analyze this a bit more carefully, then the expected running time is good. It's n plus m, like Knuth-Morris Pratt. It's expected here because there's some part is missing. How do you choose a suitable prime number? And the expectation here is essentially over random patterns or random texts. So you have to make some assumption here. Otherwise, the worst case is still m times n. You could have just many false positives from the hash. Remember, the standard time that I present here is just to find the first occurrence. You also get this running time for reporting all matches. It's harder to avoid in this case. Other good things is that this kind of string matching can easily generalize to other more complicated scenarios, like finding patterns in a picture, in a 2D array. And it uses constant space, at least independent of m, which all the other methods couldn't do. I have one last question to check your understanding. I don't know if we have time for it. No one has stormed the room yet. This is just to test your understanding. If you have to run to another lecture, then I'm fine with you doing that. For those who have a minute, I'm happy to discuss the answers for that. I know I ran through this subsection a bit too fast. It will not occur on the exam if that helps you, at least not beyond this superficial level that we discussed. Just turns out to make a really terrible choice for exam questions anyways. Obnoxious to mark. Okay, I'll wait for 50 again. Three more. Two more. One more. All right. So to quickly cover this, we're talking about Rabin Karp without the extra check. We just rely on the hashes. The algorithm never misses an occurrence, because if there is a mismatch at a position, well, the only thing that can happen is that the hash is equal to the pattern hash, but there's no occurrence. But we never miss an occurrence. But we might report positions that are not hashes, not actual matches, just because the hashes collided. In this case, we do get the best possible worst case runtime, just because we don't ever do the check. So we just run through, shift do the recompute hash in each step, and that's constant time. It does depend on M though, because you have to compute the hash of the pattern, and you have to get the rolling hash started off. So for that, you need M time. For the absurd case that the pattern is much longer than the text, that would make a difference. All right, see you on Wednesday.